All right, guys, welcome back. Welcome to Wednesday, halfway through the week. All right, so your homework was 10.8. They were all figure out what the loci was. If you have any questions or specific questions on the homework, we're not going to grade it today. I want to make sure we have enough time to get through this class. I'm going to do a little bit something different for today. So as long as you did your homework, just marked, you can put whatever you want on the Google Forms for how many you got right or wrong. I trust you guys. We're going to get right into the class so that we have a maximum amount of time. I don't want to have a video that's 50 minutes long. All right. So we're going to do a chapter review today, unlike what we normally do where I hand out the chapter review and you do it and I hand out the answers and you check your own work. I'm going to work through half of them, roughly half of them, maybe the odd ones, and then I'll give you the even ones tonight for homework. So that way you don't have that much homework. So here's your homework. There's going to be one proof. It's number 17. It's pretty easy. I'm going to have to explain to you a little bit at the end of this video of where a specific thing is. For some reason, my student edition book does not label it. My teacher edition does. So I'll give you a quick explanation on number 17 before the end of the class. Okay? All right. So what we're going to do is we're going to work through the odd ones. I think I'm going to do almost all of them. I think I skipped one. One at a time. So you notice there's the question. What I'd like you to do is read the question, put it on pause, see if you can answer it. Put your answer in Google Forms and then come back, play the video. If you need a hint, play a little bit of the video. Try not to play the whole darn thing. Try to get to the answer without having to hear the whole darn explanation yourself. Okay, so go ahead and do that. Okay, let's see what you got. So these are always, they seem like these should be simple questions, but sometimes it can get tricky. So it says a quadrilateral, 4 sides, always, never, sometimes has 4 obtuse angles. Well, I can draw one with 2 obtuse angles really easy. That's rhombus has 2 obtuse. Some trapezoids have 2 obtuse angles. Well, I should say most do, except for the right trapezoid. The question is, can you draw one with 4? Well, one way to prove why you can or cannot, or sometimes can, is to think about way back chapter 3 or 4, we talked about the interior angles of polygons, specifically quadrilateral. Do you guys remember what's the formula for interior angles of a polygon? I think Lily or one of the Lindsays always can remember this. I believe that's who remembers it all the time. And it is probably one of the more popular formulas. A lot of times you'll see it on a resource card for PSAT or SAT, ACT. So if you remember right, the angle sum of any polygon for the interior angles is n minus 2 times 180, where n represents the number of sides or angles that the polygon has. So if a quadrilateral, which has 4 sides, 4 minus 2 is 2, 2 times 180 is 360. So for any quadrilateral, the sum is 360. So use that bit of information, and that should be all you need to figure out whether it's always, never, or sometimes. All right, last hint. So let's see. Could it ever have 360 degrees? Well, let's see. Well, we know that a rectangle has 4 right angles. So there's one. So if you tried to make one of those angles more than 90, and remember that's with all of them started off as 90. If you try to make one of them more than 90, then you're already over 360. So we need to have all 4 of them over 90, which if we can't even get one of them over 90, there's no way of getting 4 of them. Therefore, this can never happen. It can never happen. All right. I was supposed to tell you, or no, I did tell you to answer this in Google Forms. All right, good. So we're gonna do all the questions like that. I'm gonna show you the question. You're gonna try to get to the answer. If you can, put it in Google Forms. It's gonna talk about boxes, box 1, box 2. I labeled the questions as per the book on page 421. So the box and the question number won't match. You'll be able to figure this out. Okay, second question. Go ahead and put it on pause, read the question, see if you can get to an answer. If you can, great. Play it and find the answer. If not, don't play the whole thing. Try to get a little hint, hit pause, and try to finish it yourself. Okay, so let's see. This one's a little complicated. You definitely probably want to draw a picture. So it says if arc AC on circle O and arc BD on circle P have the same measure, then arc AC is always, never, sometimes congruent to arc BD. Well, one thing I do is I'm just going to start straight from the start, left to right, draw the first picture. So it says circle O with arc AC. Circle O with, it doesn't tell us how big the arc is, but it does say it's smaller than a major arc. Or so I'm going to just draw, a convenient one, 90 degrees. So there's my circle O with arc AC. If I drew another circle exactly the same except labeled the points differently, then there's circle P with BD. Therefore, both arcs have the same measure. They're both 90 degrees, right? Remember, arc measure means the angle measure. How far does it go around the circle? So that's the arc in degrees. That's how many degrees. So both of them are 90 degrees. So therefore, they are certainly congruent, right? Like if you were to measure the distance between A to C and B to D, you would certainly find out that they're congruent. Well, there's one way. So that's certainly a sometimes. So we can eliminate never. The question is that always true? Is there any other way to drawing that picture so that AC does not have the same distance as BD? And the answer is sure. Just make the circle smaller. Now, clearly, BD is not the same size as AC. However, okay, here's where the words get confusing. The measure, remember, measure means angle measurement. Their angle measurements are the same. They're both 90 degrees. So arc AC is 90 degrees, arc BD is 90 degrees. But those arcs are clearly not congruent when we talk about their distance. Next chapter, we're going to actually measure their distance. But for right now, we just can visually see clearly they are not the same measurements. Okay, I shouldn't say the word measurement because that deals with angles. Yeah, they don't have the same distance. Does that make sense? So therefore, the answer is sometimes. Okay, question 3. Once again, pause it. See if you can finish it. If not, play a little bit of my explanation. Try to finish the whole thing yourself. And remember, you're supposed to be putting your answer into Google Forms. Okay, well, let's see what we got there. If the lengths of the sides of two triangles are proportional, the lengths of the sides of two triangles are proportional, then the corresponding angles are congruent. Well, this one I hope you all of you got. I mean, shouldn't even need a picture for this. It tells us not two sides are proportional, not one side. They wouldn't even be proportional then. But it says all of the sides are proportional. Remember, this is one of those theorems, or the converse to one of those theorems that says if the sides of any two triangles are proportional, then their angles are also congruent. Okay, so this is an always. And remember, this is what we typically do. We show that two angles of one triangle are congruent to two angles to the other one, and then therefore we can say that the two triangles are similar. And if they're similar, then all of their sides are in a proportion. Okay. How many people got that one right? Hopefully all of you. Okay, next one. Not sure why that popped up twice. Here we go. Here's the next one. All right, go ahead and read it, see if you can answer it, and then answer it in Google Forms, and then come back for the answer or come back for a little hint. Okay, so let's see. It says triangle with side lengths of 2x, 3x, and 4x, where x is greater than 0. Otherwise, it wouldn't be a triangle if your distance is smaller than 0, or 0 or smaller. Is it always, sometimes, or never acute? All right, this one requires you to do a little bit of thinking. And if you remember, I think it was 3 chapters ago when we were dealing with the Pythagorean theorem. We had that one statement, or it's actually 2 statements, where can you figure out whether it's always, sometimes, or never a right triangle? And if it's not a right triangle, is it acute or obtuse? And that's basically the theorem we're going to use. So the Pythagorean theorem says the largest side is always the hypotenuse. So I picked the largest one. I don't need to put x. They're all scaled up by a factor of x. So it doesn't matter. I just eliminate the x's. Now, if one of those was a y, I could not do this. But since they're all x, that's the same value, I simply do the problem without the value x. Okay, so 4 squared equals 2 squared plus 3 squared. Let's see if that's true. If it's true, if they are equal, that means it's a right triangle, and that's not acute. Let's see, 4 squared is 16, 4 plus 9 is 13. Clearly, they're not equal. So let's see. 16 is certainly bigger than 13. So if you do not remember the theorem, and the theorem said if the hypotenuse squared is larger than the square of the sums of the other two sides, then that is obtuse. Okay, so if it was less than, it would make it acute. Okay, so then that means it can never, ever, ever be an acute if that's the fact. If the longest side is larger than the square of the sum of the other two, then it makes it obtuse. Okay, all right, on to the next one. All right, well, there's a complicated picture right there. So it says, or go ahead and see if you can work through the problem, answer it in Google Forms. If not, come back for a hint. And if you think you got it right, go ahead and let's see if you got it right. Okay, so let's see. It says if the measure of arc AB is 80 degrees, the measure of CD is 66 degrees, and the measure of DA is 70 degrees, then angle ASD is how big? ASD, ASD. Okay. Well, I mean, even if you don't know what to do, you can always label the parts. So let's see. AB, arc AB, that's 80 degrees. Arc CD, I need smaller text or font. That's 66 degrees. And DA is 70 degrees. Notice there's only one piece missing. I don't know if I need this, but we might as well go ahead and do it. So there's 360 degrees in a circle, and I've got 80, 70, and 66. Let's see. 80 and 70 is 150, 150 and 66. All of that subtracted from 360 is 144. Okay? All right. Don't know if I needed that, but I certainly can label that. So let's see. Where is ASD? ASD. Oh, yeah. Check that out. ASD and angle BSC make that big X. We had a theorem about that. Do you remember that one? That was that last chapter or the chapter before? I can't remember. Anyway, we had a theorem. The theorem said that if you got that X, even if that X occurs in the center, that we take the sum of the two arcs, we add them together and divide by 2, and that's going to be equivalent to one of those angles, right? Do you remember if it was adding, subtracting? Yeah, this one was the adding one, right? So we take those two angles, we add them together, right? BC and DA. BC was 144, DA was 70. Add those two together, and we divide by 2. Well, if you do that, you get 107 degrees. Cool? Okay, moving on. All right, question number 11. This is box number 7. Make sure in Google Forms you're answering the one for box number 7. All right, it's question number 11 in the book. It's not question 11 on the Google Forms. All right, it's the same picture, different setup. Go ahead and see if you can do this one. All right, how'd you do? All right, so for those you need some help, or if you're checking your answer, let's see. We got RD. Where's RD? Okay, RD is 9. DB. That's the whole darn thing. I'm going to probably label it on the outside. So DB is 16. So the whole secant there would be, let's see, from R to B would be 25. I'm not going to label that. I don't know if I'm going to need that. I don't know how long SB is. I don't know how long SD is. I know the whole thing is 25. And BS plus SD equals 16. Okay. It's asking us what RC is. Where's RC? RC. Oh, I remember this one. This is that one where you have a secant and a tangent. If you need to recall, go back one chapter and you'll see what that says. And what it says, anybody remember? It says that RC squared is equal to the small piece, RD, times the whole darn big piece. Okay, times the whole darn big piece. So RC squared would be equal to RD times the big piece, which is RB. So if I'm trying to solve for RC, look at the equation I just wrote. If I'm trying to solve for RC, well, it's got a square. So how about we take the square root of both sides? If we take the square root of both sides, you'd wind up with that, yes? So all we need to do now is plug in the numbers. Do we know how long RD is? Sure do. It's 9. How about RB? 9 is 16 or 25. Those are two perfect squares, 9 and 25. Now, if you weren't paying attention, you'd multiply 9 times 25 and then figure out you got a really big number. Of course, you're probably using your calculator. But I'm saying just look at the numbers, 9 and 25. Square root of 9 is 3. Square root of 25 is 5. 3 times 5 is, that's right, 15. How many people got that? Good for you. Okay, let's do another. So this is box 8. Find it on the Google Forms, the answer for box 8. And this is 15 in the book on page 421. All right, pause the video, answer the question. If not, listen to a little hint or check your work. Okay, so it says if triangle DEF is a right triangle with hypotenuse DF. All right, so right triangle. Well, DF is the hypotenuse. So I'm making DF the hypotenuse. It makes angle E the 90-degree angle. It says DE is 16. So D is, I wrote 16. That's a mistake. It should say 6. It should make 6. I did this whole problem, found that I got the wrong answer, and I spent like 15 minutes just doing the calculation over and over again. And then I finally figured out that I labeled the problem wrong. DE is not 16 by the book. This is question number 15. DE is 6. So ignore that thing at the top there. I made a mistake. Okay, so DE is 6, not 16. EF is 8. It's a right triangle, right? So I could immediately just, I don't know, use Pythagorean theorem and find how long DF is. But we'll finish with what we're given. It says there's a point X on DF such that EX is perpendicular. So there you go. And notice you just made, you made an altitude. You made an altitude. So this is the one that you got to really be, I don't know, on your toes thinking about it. We've had this shape before. What was this, 3, 4 chapters ago, maybe 5 chapters ago? This is one of those right triangles with an altitude. We got one theorem and we got 2 corollaries from. And this is the one I always tell you, hey, remember, you always see this on tests. You do. It's used frequently. It's really easy to forget. We had 2 corollaries, right? And the corollaries dealt with, whether you're talking about the length of the altitude or you're talking about the length of the 2 legs of the right triangle. Well, let's get the hypotenuse first. Let's get all of FD. So let's see, 8 squared plus 6 squared, that's 64 and 36. 64 and 36, 100, square root of 100 is 10. Therefore, that whole darn thing is 10. So FD or DF is 10. It wants us to find DX. That's that little tiny piece. So what you need to do, flip back a lot of pages, and get to that theorem that had that one picture right there. Now notice our picture doesn't match, our triangle's flipped around, but it's still that basic configuration. You have to flip this around in your head. So if we were trying to find BC, BC would be DE on our picture, right? BC would be, yeah, that's right. BC would be DE on our picture, and then BN would be XD. Now we're trying to find DX, so that's what we're going to use. Hopefully I didn't just really confuse you. Basically, take a look at those two triangles, flip them around so they match each other. All right, so what we need to do is we need to solve for DX, and DX on our theorem triangle, that's the one that was from the book, is BN, all right? All right, so, well, I know what BC is. BC is the long leg. Well, that's ED, so ED or DE is 6. AB on our theorem, that's the hypotenuse. Our hypotenuse is 10, so the only thing I don't know is BN. BN is the long piece of the hypotenuse that's split by X, okay? Oh, by the way, that's what we're trying to find for this problem. So we'll just assign the variable X. I guess I probably should have chose a different variable. It confuses you since there's an X on the label of that one triangle. Okay, how do you solve that one? Remember, to get rid of square roots, you do the inverse. You square both sides. If we square both sides, you get 36. And remember, in geometry, we don't get the plus or minus. Okay, divide both sides by 10. Therefore, you can see that X is 3. It's not approximately 3.6. It is 3.6. Boy, that's 2 mistakes in one problem. All right. Okay, so that leaves the proof. And I just wanted to, once again,